Friends, so in previous lecture we talked about basics of pinch technology. We talked about how pinch technology can save the energy for a given plant. Not only by changing design, we can change the flow sheets and thereby we can increase the energy saving. Now in this session, let us try to see the role of thermodynamics in pinch technology. So, when it comes to thermodynamics, most of us who are involved in engineering design, specifically process engineering design, have somewhat unhappy memories thinking back to thermodynamics. So let's talk something about thermodynamics. And I'm sure that while you are learning thermodynamics, that was not sounding good, but here you will be able to have fun out of it. So either we did not understand it, or gave up hope that we ever would. And remember, we dread the horror that struck on examination day. So a day before examination, we all have our here and there and trying to mug up everything and trying to just wait for the examination or the question paper to come to us, and we just write everything on in the piece of paper and try to get relaxed at the end of the day. Or alternatively, we were amongst the chosen few whose photographic memory would allow us to reiterate the definitions of something called as entropy, gas free energy, and all those differential equations faultlessly, but without real understanding. That is important. Like you might be knowing someone in your class who were very easily able to mug up something, reproduce that in the examination, and felt like they are through, but then there was no real understanding. So thermodynamics has a very long-lasting memory in our minds. Afterwards, we could never help asking ourselves, what is it all for? What do I do with it? So that's what thermodynamics is all about. It all depends on how you look at the usage of or the application of thermodynamics. In the best of the cases, thermodynamics seem to be a fascinating science without a real application. So you might appreciate the equations and mathematics and definitions and all those Greek words, but you would never be able to actually understand the real uses of this science. However, it has an immense potential to be applied, and process integration is a very best example, you may say. Very basic thermodynamics, very very high usage in terms of industrial applications. So pinch analysis is based on a straightforward thermodynamics law, and it uses it in practical way. We distinguish between inevitable and avoidable thermodynamic losses and practical or ideal performance targets. So we set targets based on thermodynamics to achieve both energy savings and other process benefits. So let's talk about capital energy cost, right? Sometimes it is believed that energy recovery is only important if energy costs are high and capital costs are low. That means if I have a heat exchanger, and if heat exchanger is consuming very high amount of energy and the capital cost associated with heat exchanger is low, then only I think that energy recovery is helpful. But it's not the case. What we have to concentrate on is the total cost. Total cost is making the component from both the components, capital cost and energy cost both. If you can reduce the energy consumption, capital cost can also go down. So let's compare three processes, right? One process where all the things are supplied through utility, right? Cheap utility. We have got cheap utility, and we can supply the entire process with the utility. Then the second is as much heat recovery as possible if the utility is expensive. And then third is simpler network, wherein some recovery is possible based on pinch analysis. So the third one is based on pinch analysis. And how do we compare all these three? We compare all these three based on the area required, that is capital cost at the end of the day and total cost. So this is the first and foremost network. There are three streams which needs to be cooled from 300 to 200 with Cp as 1, and there are three streams which needs to be heated from 50 to 150 with heat capacity as 1. So what happens is I supply utility, that is cooling water, in all the three streams so that it goes from 300 to 200, and a steam which is a hot utility so that this gets heated from this to this. And what I do is I make the summation of the area required, which is nothing but 204. So there is no process to process exchange. It is all utility which is supplying. Then what I have is I replace those utility exchangers with maximum possible exchange of energy. So what I have is this 300 to 200 runs, what happens is this gets heated, like this gets cooled and this stream gets heated. This is further cooled and this stream gets heated, and this is further cooled and this stream gets heated. So I reach from 300 to 200 by exchanging heat with the stream which is coming up. So how many exchanges I have? 3 into 3, 9, and accordingly I have some area of the exchanger. And the third possible way is based on pinch analysis, wherein what I do is I try to exchange the energy according to pinch analysis, and what I find is that okay, I can directly connect one stream with the other stream and one exchanger at a time, and my area reduces to 133. So if I look here, the area here is 204, area would naturally be more than that, and area is the least here. Right, so this is based on the pinch analysis. So if you perform pinch analysis, right, the area requirement would also reduce along with the utility requirements. Like see, utility requirement was 0 here as well. You don't need any cooling water, you don't need any steam, but since you are not targeting based on the pinch method, your area may be more than this. So if I compare this with this, there is no utility requirement, but there are 9 exchanges, whereas here 6 exchanges, right? And here there are 3 exchanges, and naturally again no utility requirement. So this is a very hypothesized kind of a case study where we are trying to exaggerate the things. But what happens is that if you properly apply pinch, it will not only save energy, it will also save your total costing, right? So whether the energy requirement is less or more, whether the capital cost is less or more, apply pinch technology in order to gain its benefit. So you can find naturally the benefit of pinch technology. So the total surface area of the design were evaluated. The network for minimal capital cost turned out to have the higher total surface area and is more expensive in terms of capital cost as well as operating or energy cost. Why costs are higher for a minimum capital cost network? There are 2 basic thermodynamic effects influencing capital cost. What are those 2? One is the driving force, another is the heat load itself. We know what is driving force. Driving force is delta T, right? As we reduce the driving force, we need less utility and the overall heat load decreases. So if your delta T is less, right, your naturally the energy requirement decreases, but your capital cost will increase, right? Capital cost will always increase with reduced driving force because delta T decreases, but capital cost also decreases with reduced heat load. So if your delta T is reducing, though the capital cost might increase because of the area requirement, but since the load itself is less, right, the capital cost increase can be compensated. What I'm trying to say is this: we all are associated, like we all know this kind of delta T ln if I write, right? Now if this delta T reduces, we say that the area increases, but then this decreases this as well. So if I talk of area is Q upon U delta T. For a given system, U is fixed. So if delta T decreases, area has to increase, but along with delta T decrease, this also decrease. So this increase in A can be nullified by Q. If the Q is fixed, like if the amount of load is fixed, then change in delta T or reduction in delta T will always increase A. But if along with delta T, Q also decreases, the increase in A is nullified by that. And that is why what you need to be careful about is that the first design without process heat recovery handles twice much as heat as necessary, because you could see that all of them were supplied with utility. As a result, capital costs are increased even though the driving forces are large in the first case, right? So this is something which we have to keep in mind, right? Let us talk about some key concepts in pinch analysis, and then I think we'll call it a day for this particular session. So any flow which requires to be heated or cooled but does not change in composition is defined as a stream. So this is a process stream. Either the stream requires heating or it is cooling, but it's not changing its composition. The stream which starts cold and needs to be heated up is known as a cold stream or heat sink. The stream which must be cooled down is called a hot stream, a heat source. Now mind well, when I talk of hot stream and cold stream, because of our natural mindset, we always tend to think that hot stream will always have a temperature higher than cold stream. That's not necessary. How are we going to define cold stream? Cold stream is defined by a stream which starts cold and needs to be heated. So say for example, I have a stream which is going from 30 to 60. So this is a cold stream. And I have a stream which is 100 and going to 70. This is a hot stream. I have a stream which is at 120. I'll put hot here. I have a stream which is at 120 and I need to take it to 150. Which kind of stream is this? Cold stream, right? Because the temperature needs to be increased, right? I have a stream which is going from, say for example, 25 to 50. This is a hot stream because see, anything which can give you the energy is hot stream, and that's why it is also named as heat sink and heat source. So this is heat sink and these two are heat sources, because while they reduce the temperature, they give you the energy, right? So please be careful about this, that hot streams here are not necessarily having higher temperature than the cold stream, right? Naturally, when we want to give away the energy from hot stream to cold stream, we have to make sure that the temperature is higher, but not in the process entirely that hot stream is always having temperature greater than cold stream. Please keep this in mind, and this will help you to understand the certain things as we move further. The initial temperature is always termed as a supply temperature, and the final temperature is termed as target temperature. I think that is fine and fair, not to discuss further on that. For every stream, we need to calculate enthalpy at various temperatures, and when you plot that enthalpy as a function of temperature, in fact temperature is a function of enthalpy, that is termed as temperature enthalpy diagram, and this will will be plotting energy of a stream at a given temperature. So this is your temperature enthalpy diagram. So there is one stream, another stream, and you can see that these are your delta H or H, and this is your temperature. So we will discuss about this more in the next session. I think we have been able to explain the key concept in pinch analysis. Thank you.